Oh, hi there. I am Karen, an artificial intelligence voice from Google. I'll be talking you through the coming slides. In this presentation, we'll be discussing the Egel language and interpreter. We'll dive into the graph semantics, how Egel programs are evaluated, explore the language, review the current state of the interpreter, and set some future goals. The Egel language is an untyped concurrent functional scripting language based on eager combinator rewriting. But that's not all there is to it. What we really want to do is explore and exploit a trivialized semantics for a functional language, so most of this presentation will be on that topic. Let's dive into a bit of history and go back approximately 75 years. At that time, researchers were investigating how to create useful languages, and one of the primary questions at that time, though it looks innocuous now, was how to evaluate expressions. Once you can do that, you can start designing programming languages. So the first step is to write down an expression and its tree representation and ask yourself how you'd design a machine that would evaluate that. As time progressed, for functional languages, a number of solutions were invented. The early venerable Lisp compilers concentrated on an operational semantics around lists and direct compilation of expressions and words to assembly. Meanwhile, or a bit later, academics and mathematicians were looking for more math-based machinery and came up with the SECD and CAM machines for evaluating lambda calculus-based languages. SECD is mostly of academic interest, but CAM was used for the implementation of the well-known OCaml language. Miranda, another old language and predecessor of Haskell, was based on a combinator language, recognizing the close kinship of lambda calculus and combinatory calculi as trivialized models of computation. In more modern, lazy functional languages such as Haskell and Clean, term rewriting of combinatory calculi were generalized into elaborate graph rewriting machines, notably the spineless tagless graph machine and the parallel ABC machine. We're going to take a step back, pretend we live in the 70s, and most of this is in its early years, and develop a trivialized operational model closely related to all of the above. Remember the mathematical representation of a term a few slides back. On this slide, we show a more computer-friendly or a bit more compact representation of that. Terms are either primitive objects or arrays of terms. What we still want to do is multiply the addition of 2 and 3 with the increment of 1. Now for the magic, instead of developing an elaborate usually stack machine, we're simply going to change the representation of the term graph by naively following our mental steps during the evaluation. The first step is to recognize that the expression contains some work in the fur of reducible expressions, also named red x's. These red x's can be evaluated in a specific order, and that is what the dotted lines signify. We'll start in the lower right corner. Red x's may take arguments. Those are pointed towards, but a red x also has a result, and that result should go somewhere. The solid lines pointing upward at empty boxes show where the result should go. We twisted the representation, though evaluation is straightforward, and we'll come to that later. I colored the pointer to the root of the graph red, and there's something going on there. Following that pointer, you won't find cycles. We started with a directed acyclic graph for an expression, and twisting the representation to elaborate the evaluation didn't change that. Please take a moment to convince yourself that the shown graph is still a directed acyclic one. Now we'll investigate the evaluation of the term graph. On the left, the original graph, and on the right, the term graph after one reduction step, are shown. Unsurprisingly, incrementing 1 results into 2, and that is placed in a receiving array. After we've done that, the new root of the graph becomes the next red x, signaling that there's more work to be done. We repeat the process for the addition of 2 and 3, resulting in 5. Multiplying 5 with 2 gives 10, and at this point evaluation will be stopped since there are no red x's or work to be done left anymore. We have shown how to evaluate small mathematical expressions, and that was all pretty much straightforward. But how does that give the machinery for function evaluation? Let's go to the next slide. Let's inspect the, I assume, well-known rule for the faculty function. The thing to recognize is that a regex, a statement of work, might result into more regexes or work to be done. So, given that rule, with a bit of tinkering, we should know how to translate one step in the evaluation of a concrete instance of that rule. The regex is rewritten to a number of regexes. Fac of 5 will result into 3 regexes that will decrement, compute the next fac, and multiply the result. Basically, any work will result into more work to be done, or some result whereafter the remaining work will be done, and this all while maintaining the acyclic invariant. You can take another moment to convince yourself that the above expansion didn't introduce cycles. Given the operational model presented in the previous slides, we have the mental model of the machinery capable of evaluating any Turing-capable functional language. Despite that, one might find the need to express complex control flow directly in the term graph. Egel, as an experiment, implements a bit more elaborate model that mimics exceptional control flow through handlers. Every thunk containing a regex is again expanded with a special field referring to the exception handler for that expression. In the picture, an example is shown. For clarity, the handler pointers are colored green. The addition and throw regexes are a part of the term that operate within a context of a given handler. The identity function and subsequently their exception fields point to that handler. The exception handler itself refers to the exception handler of the outer context. Throwing a value corresponds to applying the exception handler to that value within the given context. And of course, the resulting graph is still directed and acyclic. We'll not delve too much into concurrency issues of this semantic model, but leave it at that concurrency comes easily by just instantiating multiple roots that will each reduce their part of a directed acyclic graph. So far, I hope the examples given have convinced you that we've presented a model where evaluation can be achieved through trampolining the root node of a directed acyclic graph. But given that, what did we learn from that, and what can we actually do with it? For starters, we can implement a functional language that exploits the model and shows that it actually works. But apart from that, it's a very strong invariant on a trivialized model that showcases, relates, and clarifies a number of things. For example, we may want to know why stack machines were a solution in the first place, and this model, by making explicit what work should be done in what order, clarifies that. It also closely relates compiling with continuations to graph rewriting. We couldn't come to see thunks as heapified stack frames, or we might be stuck proving that effect handlers cannot form cycles and refer to this model. A small toy implementation in Egel could be used to provide some evidence for that. Let's see how we could exploit the model. For one, a concrete machine can be implemented with reference counting. And reference counting is appealing for a number of reasons, primarily since it's a local operation, whereas most other schemes invest a lot into hiding that they need to scan the entire memory to collect. Then this model rewrites, so there's less need for tail call optimization. If you term rewrites to another term in constant space, then that's all there's to it. Furthermore, this is a trivialized model where at any point in time the program state forms a graph that can be serialized or shipped. That's not new. Other languages can do that too, but it's made very easy. A pleasant property of the model is that when terms go out of scope, they are immediately collected, and that allows for a scheme where finalizers clean up resources. You'll never need to worry anymore whether a file handle is closed. The Egel language is a bare-bones front-end to the previous semantic model. It is untyped on purpose. When exploring an operational model, it just makes sense to not place too many restrictions on the programs you can type in. Since we don't want to place restrictions on programs, we actually go the other route of relaxing as many constraints as we found useful. That comes at a performance cost. It also means at any point in time you can easily shoot yourself in the foot. However, we're not totally leaving the academic ivory tower. People will recognize that the Egel language is close to a lambda calculus with constants in the coming slides. To start of, primitives. These are the usual suspects of integers, floating point numbers, Unicode character or code points, and Unicode strings. Since Egel is untyped, constants compose. The series of 0 and 1 or cons a nil roughly denote the same thing, a composition of two or more constants. The workhorse of the Egel language is the anonymous pattern matching rewrite. Variables are always in uppercase to discriminate them from constants. You can either bind variables or match against constants in a pattern. The pattern matching rewrite may consist of multiple alternatives, in which case they are matched in order. Different from other functional languages, a pattern matching rewrite in Egel can be a mix of any arity. Let is just another form or syntactic sugar of such a rewrite. Combinators come in two forms, constants or functions. We might want to introduce constants to create certain data structures through composition. Then, of course, we need functions. Functions are usually expressed as being equal to certain pattern-matching rewrites, and may be recursive. Egel programs can primarily be seen as a collection of constant and function combinators. For brevity, Egel has some syntactic sugar for often used data structures. Tuples are written in the conventional manner, but underwater are constant compositions. Instead of spelling out list with nil and cons constructors, curly braces can be used. As explained in the operational model, it's easy to support control flow operators and concurrency, and we have implemented exactly that. Try and catch is supported. Any Egel value can be thrown and caught. The one concurrency operator we support is async and await. Note that the argument to async needs to be deferred with a lambda to make sure it'll be processed in its own thread. Egel has provisional support for namespaces and modules. Modules behave similar to textual inclusion of the file referred to. A transitive closure is calculated for all imports that deals with possible cycles. Namespaces separate naming concerns in the standard manner, though support is rather rudimentary at this point in time. The example ties it all together. The prelude module is imported. The Fibonacci function is defined in its standard recursive form in its own namespace, and a main function drives the script. The previous slides showed the gist of the Egel language. Of course, there is more. Though the Egel software is still in an alpha state, we dabbled with various extensions and libraries. Mutable references and mutable dictionaries were included for performance reasons. Through mutation, it's possible to create cycles in the term graph, and those won't be collected. We added pipes and do notation. It's the preferred manner of dealing with function application chains in Egel. Literate programming is supported, though again rudimentary. Egel will just blindly execute code blocks in a markdown file. And then there are various libraries in which we dabbled with regular expression, remote execution of Egel programs, and a Python bridge. The Egel interpreter is implemented in C++. This allowed us to rely on C++'s native reference counting and implement the interpreter without a garbage collector. In the source code, combinators form a complex object-oriented hierarchy. In order for people to make it easy to include Egel, it is distributed in a header-only manner. The uncompromising relaxation of constraints in the Egel language, as well as the operational semantics, as well as its naive C++ implementation, bring a substantial performance burden. Egel programs are very sluggish compared to programs in other languages, and the interpreter also isn't very user-friendly. At the moment, Egel isn't very useful except for experiments and short scripts. Egel programs are written in a dynamic manner, so we want to concentrate on shortening the feedback loop with better error and tracing messages. We made a number of costly design decisions, but are sure we can mitigate those. At minimum, we want to prove that the elaborated operational model can be made very performant with a typed backend. And that ends this presentation. Thank you all for watching.